have here. I'm very happy to introduce Dr. Kilpatrick. He did his PhD from University of Arizona and then moved to UC Santa Cruz for his first postdoc, and then moved to Northwestern for another postdoc, and now he's a research faculty there. We have been collaborating for quite some time now, so he will be talking all about some of the work he has been doing with multifaceted astronomy.
Thank you, Manisha. It's great to be here at Monash in Australia, where it's very warm and welcoming and bright and away from the cold and bitterness of Chicago. I've really enjoyed my time here. I was last week in New Zealand at a conference on transients, and just thank you for welcoming me here. I'm going to be talking about some of my research on multi-messenger astronomy, neutron stars, and a topic I've been interested in really since I did my PhD at Arizona on where do the elements come from in the universe. And I think on that topic, we've really had a there we go. Okay. So we've been extraordinarily successful in astrophysics explaining the periodic table, and where the elements come from. So, of course, as you learned in your Astro 101 classes, Big Bang nucleosynthesis explains the lightest elements in the universe. Some of the metals in the second row of the periodic table were also synthesized, but many of them are created through cosmic ray spallation and sort of spontaneous fusion in the interstellar and intergalactic medium from high-energy particles accelerated in supermassive black holes and supernovae. Sort of intermediate mass elements and carbon are generated in the cores of these intermediate mass stars. So sort of central engines of nuclear furnaces coupled to these conveyor belts, which dredge up elements, including some of the heavier elements that I'll get to in a bit. But mostly carbon and nitrogen are synthesized in these stars and just sort of spewed out into the interstellar medium. Supernovae, I'm very interested in, explain a lot of the intermediate mass elements, especially oxygen. They're the big oxygen producers in the universe, and other alpha elements, all the way up to about titanium and a few of the other heavy elements beyond the iron peak. And then, of course, the iron peak itself is generated from thermonuclear supernovae, or these carbon and oxygen white dwarfs are just like loads of dynamite. We light a match, they synthesize these heavy elements in the middle of the periodic table. But until about 10 to 15 years ago, this was sort of the state of the art. And we weren't able to very effectively explain where in the universe these very heavy elements that have a lot of historical, commercial significance. I'm sure you have some of these on you: silver, gold, platinum. We didn't really know exactly where in the universe these were coming from. And this was a very challenging problem in astrophysics to explain how do we synthesize these elements. And I'll explain why. So as you look at sort of the map of isotopes in the not the periodic table, but looking at increasing neutrons on the x-axis and protons on the y-axis, most elements in the universe are synthesized just by pegging these heavy elements with neutrons and slowly building them up. So that happens, one neutron at a time until the element becomes unstable. It undergoes a beta decay, and you increase the number of protons and the atomic number of that element, synthesizing a new element. But you can't explain this way these sort of islands, these stable elements that aren't directly connected to this valley of beta stability in this way. So we know that there are stable elements here. I'm showing xenon. There are many examples of this that can't be explained via this sort of slow neutron capture process. So just to show that in another way, if I slowly bombard heavy elements with neutrons, they'll build up to heavier and heavier elements until the element becomes unstable. Beta decay will happen. You'll increase the atomic number. So instead, in order to do this, we really need the R process, so the sort of the opposite of the S process, where the time scale for capturing neutrons is much, much faster than the time scale for a beta decay. And you can sort of skip over these islands of instability or instability over to islands of stability and produce these heavy elements that we can't explain in any other way. So how do we do this? Where in the universe can the R process occur? Well, of course, one of my favorite papers and really required reading, and again, sort of Astro 101, the synthesis of the elements in stars. If you look toward the end of the paper, I think this is actually in section 8 of the paper, Margaret Burbage says that if you have the pure neutron core of a star and some sort of instability occurs and rips off enough of this very neutron-rich material, you can excite the R process and build up these very heavy elements. And so for decades, really going back to 1957, even before we knew about neutron stars, this was the idea and sort of the motivation for looking for the astrophysical side of the R process. But really the question was, what is the observational signature we should be looking for? Where in the universe can you excite one of these instabilities on the neutron-rich core of a massive star and cause the R process to occur? So again, just showing this sort of diagram, these neutron-rich cores are produced in very massive stars from the sort of proto-degenerate core, iron-rich core of a massive star. Supernova explosions happen, and you can create a bare neutron star, this sort of reservoir of neutron-rich material where we think that the R process can occur. And so really another famous astronomer about 10 years after B squared FH discovered the first neutron stars. We know that they had to be extremely dense compact objects because they were discovered in radio waves as these sort of millisecond time scale coherent pulses of radio emission, indicating to us that they had to be extremely compact. So consistent with this prediction from Margaret Burbage that these are extremely dense cores of massive stars. And so we had, for the first time, localized this sort of site where you have one of these reservoirs of a lot of neutrons. And really the question was, how do you excite this instability in order to release enough of these neutrons and excite the R process in the universe? So this is just an example of one of these cores of massive stars. We know from X-ray observations that they have to be about 10 kilometers across in radius. This is just showing neutron stars that would look sort of hovering over the San Francisco Bay, but you can imagine this sort of being Port Phillip right below Melbourne. This is a city-sized dense core of a massive star, the mass of the sun, but all condensed down into a source just a few kilometers across. So sort of the next ingredient explaining how this instability can occur in a neutron star, I'll just tell you a little bit about the way that massive stars form because of sort of the gene's mass and extremely dense molecular cloud cores. We think that massive stars, and in fact, we observe directly that massive stars tend to occur preferentially in binaries. So this is increasing stellar mass on the x-axis and the fraction of stars that have at least one companion on the y-axis. And these stars are the ones that we think are producing these neutron stars. We observe from supernova remnants in our own galaxy that their explosions tend to have very compact X-ray or radio sources in the center, consistent with neutron stars. So we think that if you can maintain the binary after two supernova explosions occur, you'll be left with two neutron stars. And sort of if they spin together via gravitational wave radiation, they can crash into each other and cause one of these instabilities where the R process can occur. So just showing that in the form of a movie, you have two neutron stars. The supernovae have occurred a long time ago. They're inspiraling, they're emitting gravitational waves and losing energy, and then eventually they crash into each other, causing a gamma ray burst, this bipolar outflow, and then a more isotropic transient source, which is where we think most of the R process is occurring. So you've ripped off enough of this material that the R process is excited in the ejecta, and you can produce a very significant amount of the R process. So how do we find these sources? So the major science question that I'm going to be answering today are sort of what is the observational signature of this scenario, this neutron star merger, and how do we know that the R process is occurring in it? How do we distinguish this from other astrophysical phenomena like supernovae that I've talked about? Sort of what new surveys are needed to find these signatures, because these are very elusive events, and I'll be talking about some of the techniques that we've used in order to identify them and find these R process-bearing transients. And then in the future, what is the prospect for isolating sort of large populations of these sources? So this is very ongoing work that Manisha and Connor and I are all involved in, trying to find the R process in large volumes of the universe. So just to get started on the first of these questions, what are the observational signatures of the R process? How do we know that they're occurring in these neutron stars? And how do we distinguish them from other astrophysical phenomena that we all sort of study every day? Are they actually producing the heaviest elements in the universe? Is there some diversity in these sources and different distributions of yields that we should expect? So this is just diagrammatically showing you one of those neutron star mergers. You have two sources that merge together. It might produce a black hole. In this scenario, it might produce a long-lived neutron star, maybe even a very exotic neutron star like a hypermassive one or a magnetar. It excites this bipolar outflow that causes a gamma ray burst, about a 0.1 to 1 second or maybe up to 2 second transient, possibly even longer, that we observe with gamma ray satellites, and that we've seen all the way going back to the 50s, where the first gamma ray bursts identified, but we didn't necessarily know that they were associated with neutron star mergers. And then this very unique transient called a kilonova is the source that we're actually looking for. It's a very faint, elusive transient that I'll talk to a bit about. But this is where we think really all the ejecta and the R process is occurring. All the free neutrons are bombarding heavy iron isotopes in these ejecta, causing these very heavy elements to form. So the way that we find these, of course, LIGO is a gravitational wave interferometer with one arm based in Washington State and another in Louisiana. And there's about a 3,000 kilometer baseline between the two. They're able to see the actual gravitational wave radiation, these ripples in space-time as they propagate through the universe and cause a perturbation in these long laser arms, these interferometers, that are, there's two arms in both Washington and Louisiana. They interfere with each other, and as a gravitational wave passes through, we see a characteristic in-spiral or ripple signal in the laser itself. And so because there are two of these arms, we can localize them to a specific region of the sky. It's sort of like your ears, where you can tell if a sound is coming from in front of you or behind you, but it doesn't localize much better than that just using LIGO itself. And because compact objects themselves have a very strong gravitational quadrupole moment, we're able to very efficiently see these sources within some volume of the universe. So the more massive the object, the much more distant we can see them. And that's why LIGO is very good at seeing black hole mergers, not quite as good at seeing neutron star mergers, and it can't see white dwarf mergers at all. So just sort of diagrammatically showing how LIGO works. This is the strain signal, the actual measurement that LIGO is making from the in-spiral of two compact objects from the first detection of a binary black hole merger that they saw back in 2015. So as these objects are in-spiraling due to gravitational waves, they're losing energy, and the in-spiral gets faster and faster until they eventually merge together. And they're still looking for ring down signals from some sources that hasn't quite been observed yet. But this is sort of the template that they use to match to the sources So the direct measurements that LIGO can make are the masses of the sources, and then actually the distance to the source comes directly from this sort of template matching between numerical relativity models that they have and then the actual strain data. So it's a very clean measurement. It's the best way to measure mass directly, any astrophysical observable that we have. And it's also very efficient at measuring distances to objects using this same method. So back in 2016, I'd just gotten back from a meeting in Copenhagen, and it was 6:30 in the morning, so I admit I wasn't awake yet. But right when I woke up, I got this alert from the Fermi Gamma Ray satellite indicating that they had found a gamma ray burst coincident with a gravitational wave source. And because of the coincidence between these sources, the false alarm rate, or the rate at which this would just happen by random due to chance or noise, was estimated to be about 1 in 10,000 years. So we knew immediately that not only does this match the kind of source we were expecting to yield a lot of our process elements, a gravitational wave source coincident with a gamma ray burst, but this was very likely to be a real event, so something that we should be following up. So this was the actual prompt data, or just a visualization of it. LIGO said there was a roughly Chandrasekhar mass, 2 neutron stars merging together. So they saw this very characteristic strain. Oops. And then 2 seconds later, they found a gamma ray burst with a Fermi, and actually another satellite integral saw the same gamma ray burst. So this was a very weak gamma ray burst, but consistent in duration with what we expected for a neutron star merger, something we've seen many, many times before. But it was somewhat weak, we think, because it was pointed slightly off axis from us. And that was actually corroborated by the gravitational wave data. You can independently measure sort of the angle between the plane of the gravitational wave merger and the jet, we think, of the gamma ray burst itself. So just from these data, we knew this was very interesting, something that we should be following up with our ground-based telescopes in order to find this expected kilonova signal that we expect to see. So how are we going to do that? Well, we use the localization region that LIGO also provides to us. So you see from these events, all of which were binary black hole mergers detected before the GW 170817 event that I'm talking about right now, they were localized to huge fractions of the sky. But extremely lucky for us, just about 2 weeks before GW 170817 happened, another interferometer turned on in Italy called Virgo. And you can imagine this, just like LIGO as our 2 ears, Virgo is sort of like if you have another ear on your head or on your foot. You can much better sort of triangulate where the signal is coming from. And Virgo was able to contribute to that signal and tell us it was coming from a very precise patch of the sky. So not precise in terms of the size of sort of optical transients that we're used to finding, but very precise for a gravitational wave event. And we were lucky enough to test out Virgo a few days before that, because this GW 170814 event, a binary black hole merger, had also been discovered, which we were actively following up at the time and looking for counterparts. But as soon as 170817 happened, we dropped everything that we were doing and started trying to find the optical counterpart. So this is just showing on the entire sky. This is all 40,000 square degrees of sky. This is the localization region of GW 170817. So it looks like somewhat of a tiny sliver, but it was still fairly large, again, compared to the localizations we're used to for typical supernovae or other optical transients. So my colleague Dave Coulter and I, we were using the SWOPE telescope in Chile. We were also extremely fortunate because it landed within the patch of sky that was far enough away from the sun where we were able to observe it at least for a couple of hours before it would set below the horizon and we wouldn't be able to see it anymore. So this is the size of the SWOPE camera just compared to the size of the localization region that LIGO gave to us. And so because the SWOPE camera couldn't just tile this entire thing very efficiently, Dave and I had been pursuing a new strategy up to that point to just compare this localization region to galaxy catalogs and only target the mass in the universe that we thought was at the right distance to host this kilonova counterpart. So rather than just very systematically tiling this source, we only targeted the regions within it where we thought the kilonova could be hosted. So I'm showing just individual pointings in the galaxies that we targeted. We were taking image after image within a few minutes after sunset. And in the ninth image, we found this. So this is just a very small part of our ninth image showing this galaxy NGC 4993. It's a fairly early type galaxy, which means it had a lot of old stars in it. Probably its last bout of star formation was about 1 billion years ago. But overall, the vast majority of the stars in this galaxy were billions and billions of years old. But you can see just in this image, there's not a source in our template image, which came from the dark energy camera. And using a pipeline that I built, we were able to perform just digital image subtraction and identify this source. So, okay, great. We found a transient source. It was in, this old galaxy. We find type 1a supernovae in galaxies like that all the time. How did we know that this was actually something interesting that we should be following up? Well, before we went into all of that sort of analysis, Dave, who I'm showing right here, and I wrote a circular, so sort of the same circular that alerted me to this event in the first place. We said, hey, there's this source within this galaxy. Other people should probably follow it up and get data on it. We don't really know what it is, but here are the approximate coordinates on the sky. We called it SSS 17A for SWOPE supernova survey. We hadn't really found any other supernovae that year, so it was nice to just name the source after our program. So, as I said, really the big question was, how do we separate what we were looking for, all the gold and R process elements, from iron, like in this type 1a supernova at the top from another SWOPE image, or rocks, which also occur very frequently in our images due to asteroids in our own galaxy. These are very common sources of, I guess you would say, contaminants when we're searching for gravitational wave counterparts. And so how did we know the source that we found, which occurred in a galaxy that could very easily host a type 1a supernova, was not just some other type of interloping transient? So we like to say in optical astronomy that the spectrum is the truth. But when we obtained our first spectrum of this source, it was basically featureless. This is blue light here on the left-hand side and red light on the right-hand side. And you can see that the source was very blue. It was basically peaking in the blue optical. So that was very weird to us. If you just showed me this spectrum without telling me anything else about it, I would have assumed it was a core collapse supernova, so one of these massive star supernovae that we see all the time in optical surveys. But that's also kind of weird because, as I said, this galaxy is very, very old. So its last bout of star formation was many billions of years ago. We don't expect it to be hosting very many massive stars. It would have been very unusual to see a core collapse supernova that looks like this in this galaxy NGC 4993. So then the next thing that we actually noticed about it as we obtained more and more follow-up data was that it evolved extremely rapidly. So this is the first spectrum that we obtained in the blue about half a day after the gravitational wave merger. And within about 5 days, it had evolved to be extremely red, so that almost all of its light was no longer in the optical where we could observe it with our typical optical telescopes and spectrographs. So basically, all of its SED had shifted beyond what we could very easily see with typical instrumentation, which is also kind of weird. So the reason for that is basically all radioactively powered transients can be explained just with essentially 3 parameters, modulo a lot of other very complicated physics that I won't get into, but I'm happy to talk about later. So this is attributed to one of my PhD advisors, Dave Arnett. Basically, there's three phases in a radioactively powered transient. The expanding fireball, where it's sort of homologously expanding outward. The photosphere is entrained in the fastest moving material that's outermost. You can basically explain it just as an expanding shell. And then actually what Arnett's law says is at the peak of a light curve, the total amount of radioactive material, which is essentially the total ejecta mass in a radioactive transient, is proportional to the total luminosity. And then as it declines, that decline rate is proportional to, again, the total ejecta mass and opacity, which tells you something about what that material is made of, and then this velocity term. So if you know these three parameters, you can essentially describe any radioactively powered transient modulo a ton of physics that I won't get into right now. So the next thing you should really understand about kilonovae is that their opacity is very unusual for most transients that we expect to find. So most transients like core collapse supernovae and type 1a supernovae, they're made of material like iron at the heaviest, which the opacity profile as a function of wavelength is right here. So you can see that it's never much more than about one opacity unit, 1 centimeter squared per gram in the optical or infrared. And in fact, there's a floor for ionized transients where due to electron scattering or Thomson scattering, the opacity doesn't really get below this level. But for our process transients, because they're very heavy and they have these open F shells, again, at the bottom of the periodic table, if you remember your electron physics, their opacities are extremely high. So especially if they're made of things like lanthanides and actinides, these elements at the very bottom of the periodic table, they'll have opacities that are huge compared to basically anything else we see as astrophysical transients. So the consequence of that is that these events will be extremely red, and the red light curve will be relatively slowly evolving. So it's possible that they'll have this blue emission, but it'll very rapidly transition to the red, like I showed you in the spectra, and the red light curve will also evolve a lot slower than the blue light curve. So that's actually exactly what we observed. So knowing nothing about kilonovae before this event, or having never seen an event, these theoretical models generated by Dan Kaysen at UC Berkeley were able to not perfectly, but very well explain the slowly evolving red light curve and then this very rapidly evolving blue light curve. So essentially, we modeled this kilonova using two components, this more iron-like blue kilonova model with a couple hundredths of a solar mass of material, and then this more typical red kilonova model that we were expecting to see with a little bit more ejecta mass. And it almost perfectly matched Dan Kaysen's models. These models have since been developed very heavily against this transient, but they were developed even before we knew about this sort of kilonova. So they performed extremely well compared to just what we were expecting theoretically. So can we explain all of the art process elements in the universe using this kind of kilonova? So that was kind of the purpose of the paper that we were writing, really the big question that we were trying to answer. We just did sort of a back of the envelope calculation saying, if you assume that these kilonovae are happening at some fiducial rate based on the 1 kilonova that we measured, so this is very uncertain due to Poisson statistics, but we could estimate a rate of about 25 per megayear in a Milky Way type galaxy, just using the age of the Milky Way galaxy and then the ejecta mass that we measured in this red kilonova emission, and compare it to the galactic budget of our process materials. We can measure this directly from stars in our own galaxy, and then we know pretty well what the mass of the Milky Way galaxy is. And voila, we were triumphantly claiming back in 2017 that we've solved the R process problem. And so there are a lot of assumptions that go into that. I'll get into why some of them might not be so great. But this was the state of the art back in August of 2017. We thought we had solved the R process problem and that we could explain the roughly 10,000 solar masses of R process material just using neutron star mergers. But not so fast. The R process measurements that we were making were really based on solely on these opacity measurements. And we couldn't really point to any one feature in our spectra. And this is a spectrum from Ryan Chornock studying the same transient. using these same models from Dan Kaysen, these red kilonova models, saying, it sort of looks like this kilonova, but none of these features really correspond to any individual R process element. We can't say that it's actually occurring in 0817. We really needed these redder measurements where the opacities are more sensitive to the exact composition of R process material that you have. You can more easily peer through the kilonova because it's slightly more optically thin and say that this one element appears, especially if you can observe the source at late times, which was impossible because it ended up going behind the sun. But for future kilonovae, this is what we really wanted to do, was identify specific R process elements that we could pin to our abundance measurements and say, this is the element that we're actually seeing. And then secondarily, we couldn't really explain why there was a blue kilonova component. So maybe intuitively this made sense because, just like the Big Bang started out very hot, all transients that start out from, a very small point in space are also going to be very hot just because they're very energetic. So, superficially, that can explain why there was blue kilonova emission, but there was still a lot of argument about, maybe there was a shock from material around the kilonova or a shock as it interacted with some of the tidal ejecta just thrown off. Or the GRB that we actually saw, maybe that was interacting with some of the ejecta flown off in the kilonova and heating it up, and that lowered the electron fraction in these ejecta, which sort of arrests the R process and can explain why we saw so much iron-abundant material. We didn't really know why it was that was occurring, but a lot of these predictions rely on very early blue optical and especially ultraviolet observations that we were able to get, but it would have been nice to have even earlier observations if we could get on the kilonova extremely rapidly and sort of pick apart some of these predictions and the different models for why there was blue optical emission. So that brings me to sort of what we've been doing since 2017, what new surveys were needed, especially, like I said, in the ultraviolet and the infrared, in order to explain some of the phenomena that we were observing, different R process signatures, and really pick apart these questions that I brought up in the sort of aftermath of 0817. So these were very heady times. In 2019, LIGO finished its second observing run almost immediately after 0817 occurred. We waited a couple of years. LIGO did some upgrades, and we were ready. We were raring to get more kilonovae in LIGO's third and fourth observing run. So we had networks of telescopes worldwide. We were going to do great things. The kilonova rate was going to be very high. We're going to observe so many of them, build up samples. During this time, the James Webb Space Telescope launched, so the most sensitive infrared facility that we have access to anywhere. Myself and a couple of other colleagues of mine had programs on the first cycle of James Webb in order to get very detailed infrared observations and answer some of these questions. The Swift satellite, which is kind of on its last legs right now, but hopefully gets boosted and we can use it for much longer, had dedicated programs to get the very early ultraviolet observations. The Chandra X-ray facility was going to help us. The VLA was going to characterize the afterglow of this GRB. We were just ready to do all of this science covering the entire electromagnetic spectrum, assembling large populations of kilonovae. So that's exactly what we tried to do. The next best localized gravitational wave event after 0817 was this black hole neutron star merger. So this was very interesting from GW 190814. We just plastered it with all kinds of observations, including with the SWOPE telescope, with our colleagues on Les Cumbres Observatory. Lots of people were observing this exact same event. This was also very interesting because a black hole neutron star merger, it's immediately going to already have this black hole in the center. And so some of these mechanisms that we predicted would cause a blue kilonova emission just wouldn't be there. You wouldn't have a long-lived neutron star heating up the ejecta. You wouldn't have potentially quite as strong of a gamma ray burst, being launched off of the central compact object. And so we thought this might be a much redder kilonova that we could observe. But unfortunately, we did all kinds of significant follow-up. We couldn't find anything that, definitively looked like a kilonova or 0817. And that was after vetting 189 potential counterparts discovered within a couple of weeks of the GW 1908-14 merger. We got tons of spectra. We just burned as much telescope time as we could trying to find the next kilonova counterpart to one of these events. So, oh, yeah, go ahead. Oh, so this one was, I think it was about 250 megaparsecs. So it was significantly more distant than 0817. And you're sort of getting at one of the reasons it might have been more difficult because it would have been a lot fainter. But yeah, that's a very good point. But another reason why there might not have been a kilonova is because you do have one of these black holes, and in order to get ejecta outside of the innermost stable circular orbit, where you would fling off material that could cause a kilonova, you have to disrupt the neutron star within this tidal radius that exceeds the innermost stable circular orbit. So as long as this inequality is satisfied, you'll have essentially kilonova emission, but you can see it's disfavorable for very high mass neutron stars or a very soft equation of state where the neutron star is compact. And so because one or both of those things might have been the case, the black hole was maybe about 23 solar masses, so it was quite large. We just didn't see anything, or possibly because the source itself was too faint in order for us to see. But this has just kept happening during 03 and 04. So initially, this neutron star merger rate measured directly from gravitational waves was quite high. And actually, this is just a 1 sigma measurement, so it's not directly comparable to these other measurements. But just take my word for it that the neutron star merger rate has been monotonically decreasing, mainly because LIGO just hasn't seen anything yet. And that's, the error bars are shrinking because, again, Poisson statistics gives us very large error bars. But just because we haven't seen a large number of neutron star mergers and LIGO has become increasingly sensitive, our estimate of the neutron star merger rate is getting smaller and smaller. So actually, this is creating a crisis in astronomy right now. We might have unsolved the R process problem. Yes, neutron stars can produce some amount of R process ejecta. No, that calculation that we performed in 2017 with the galactic R process budget, that might not explain all of the R process elements in the universe. But that's actually very interesting because there might be other sources that we haven't considered yet. So in the interim, one of my colleagues at the University of Chicago, Alex G., he started making very precise measurements of the R process budget in these very low metallicity galaxies. So these are sort of fossil stars generated very early in the universe and have just stuck around in these low mass galaxies like Reticulum 2. And these are indicating to us that very early in the universe, some source of the R process was required in order to explain the sort of total amount of material that we see in these fossil stars. So we need a prompt source of the R process, and for various reasons, mainly because it just takes so long for neutron stars to in-spiral due to gravitational wave radiation and eventually merge together, they're not quite as favorable to produce the R process that early on, unless there's just some mechanism that can sort of tighten the binary, like common envelope evolution or three-star interactions or something like that. So other sources like collapsars that Manisha is actually exploring through Broadline 1C supernovae have been proposed by Dan Siegel. Very recently, actually, magnetar giant flares have sort of popped up again. These are very interesting because they might power a lot of optical transients. They might be the progenitors of fast radio bursts. So there's a lot of sort of chatter in the community going on about could potentially kinks in the magnetic fields of these highly magnetized neutron stars sort of break and unlock some very small amount of our process material from these neutron stars just on their own. But we don't really know. There could be a lot of different ways to make up the budget of this R process material that we really haven't localized yet. So One mechanism that I'd like to propose as being sort of favorable for doing this is just normal supernova explosions. So we know that normal supernovae like Cassiopeia A, right here, the youngest supernova remnant from a core collapse supernova in our galaxy, has a neutron star in the center. It's observed as a compact X-ray source. We know that normal core collapse supernovae occur very early in the universe. So again, my colleague Dave Coulter just identified the highest redshift core collapse supernova ever observed at about redshift of 5, just 1 billion years after the Big Bang. And it was a normal core collapse supernova. Again, they host neutron stars, and they occur at over 1,000 times the rate of neutron star mergers, especially now that that rate we think is a lot lower than we estimated back in 2017. So that means that even if they produce a very tiny fraction of our process elements in their ejecta, they can cumulatively make a big impact on the total R process budget in the universe. So one project that I'm actively pursuing right now is looking at Cassiopeia A with, again, the best infrared facility in the world, and using mid-infrared observations to, for the first time, isolate individual elements, at least of the first peak R process, in the ejecta of this remnant. So there's this bipolar, or rather this outflow that we observe in unshocked oxygen that's associated with a much larger bipolar outflow in Cassiopeia A that we think is coming off of the neutron star from the explosion mechanism. And we hypothesize that if it's enhanced about a factor of 10 in the R process, that we'll observe these lines from germanium, tellurium, and arsenic. So all R process first peak elements that will, for the first time, tell us another site, at least of the light R process in the universe. So how am I doing on time? Okay, great. Plenty of time. So for the last part of my talk, I just like to sort of pivot back to multi-messenger observations and talk about the prospect of isolating large numbers of R process-bearing transients using a couple of infrastructure projects that I'm pursuing. One is called Teglon, based on work that Dave and I have done, and then another is Trove that Manisha and Connor are participating in. So LIGO is going to turn back on at the end of the summer. We think in late September or October. It's going to have this sort of intermediate observing run 1 with similar sensitivity to what it had just a few months ago during its 4th observing run. And this is giving us the prospect to localize more events. So we're just preparing on how to do that better. Especially because this sort of scary ghost-like O5 is a little bit uncertain right now. We don't know exactly when it's going to start. We don't know if these sensitivities that LIGO is quoting for us are actually going to be achieved because it depends on a lot of very difficult engineering work that they're conducting. But CAGRO will also be participating. We think that with more and more of these detectors, hopefully one day Australia will have one and give us another lever arm on the triangulation of gravitational wave events. We'll be able to better localize these events and more rapidly find potential kilonova counterparts, assuming a neutron star merger occurs. So one program that we're using to better localize these events is sort of formalizing the galaxy targeting search that Dave and I were pursuing using a program called Teglon. So this uses a database of all of the galaxies that we know about based on very complete galaxy catalogs out to a few hundred megaparsecs, converting them essentially into a queryable MySQL table. And then we calculate actually the completeness of these galaxy catalogs just using a Schechter function in different distance bins. So this is essentially the 3D spatial completeness of galaxies on the sky in different distance bins, just based on a HealPix format, just showing you how complete we think these galaxy catalogs are. And then finally, we can use any other kind of 2D or 3D queryable table in order to cross-match to galaxy catalogs. So for example, this is the extinction in the plane of the galaxy. You wouldn't really want to search in the plane of the galaxy in order to find kilonovae. So we can weight our observations against regions where we think the reddening is going to be very high and sort of avoid those regions. And ideally, that'll help us better optimize our searches for gravitational wave counterparts. So we've written a few papers just demonstrating the feasibility of this approach. This is one paper that we worked on actually with a binary black hole merger, just showing that these are AGN in the localization region of this source, this binary black hole on the sky. So we can use really any metric that we want to better optimize our search using this Teglon code. And we're actively deploying this in order to use sort of that distributed network of telescopes that I showed and more rapidly find kilonovae in the future using this strategy. And this is just showing if I take 0817 and I place it at different distances, this is the optimal search strategy that we would use in order to more rapidly and efficiently find the gravitational wave source. So you can see that eventually it just sort of reverts where the galaxy catalogs are incomplete to just searching sort of the center of the localization region. But at very nearby distances, like that of 0817, we know where the galaxies are, and so we can just better target those. But what I'm very excited about now is the TROVE collaboration. This is just showing all of my colleagues in that collaboration, including Connor and Manisha. But this is work that I'm leading with Dave Sand at the University of Arizona, hence all of the cactus memes in our logos. But I'd really especially like to highlight the work of University of Arizona graduate student Noah Franz and my postdoc Nick Vieira at Northwestern University, who are spearheading a lot of the development on this. So what is the TROVE? What are we actually doing with this program? Well, we know that the localization process is very hard. 0817 we were very fortunate that it was nearby and well localized, but this is a more sort of typical localization region that we would get for most events, including this very recent one from 2025 that was localized during LIGO's 4th observing run, covering sort of hundreds of square degrees on the sky, much larger than the field of view of any telescope that we have access to. We also know, again, the distances to these events. So 0817 occurred at 40 megaparsecs, where we have very complete galaxy catalogs. But we also have access to other galaxy catalogs that may be more imprecise, but go out to much further distances that we can cross-match to. And then finally, we can vet these events just using the localization region in these galaxy catalogs to rule out potential counterparts to these gravitational wave events in real time. So we did a study back in 2022 and sort of revised that study as we were preparing for TROVE and found that about 2/3 of events we could rule out just using real-time information. So even though all of these dots are different transients in the localization region of this GW 190814 event, most of them we would have been able to rule out as being associated with that event in real time just because they were at the wrong distance, they were possibly associated with a variable star or a minor planet, and that we would know about immediately after the event occurred. So if we use this information, we can better optimize our follow-up strategies and only use telescope time on the sorts of transients that we think might actually be good kilonova candidates. And we can refine that even further by using this light curve information. So again, using these models from Dan Kaysen, there may be a little bit of variability in what we would expect a possible kilonova candidate looks like. But most events, especially the merger of two Transit-Sakar mass neutron stars, should probably look like 0817, modulo the viewing angle that we see it at. So if we find an event that's at the right distance in the localization region, is not a variable star or a minor planet, and has a light curve that looks, what we would expect a kilonova to look like, we'll tell people actually quantitatively that this is the best candidate to follow up with your telescope resources and get more follow-up. So this is just sort of a diagram showing that we ingest the gravitational wave events, possible transients, these catalogs of point sources and galaxies and minor planets. We get force photometry, so this light curve information from all of these transients, and we just sort of aggregate all of that information and calculate essentially a kilonova score. So something from 0 to 1 saying, either 0, this is definitely not a kilonova associated with this gravitational wave event, or 1, we think this is the best candidate for everybody to follow. And we published a first initial study of this method using that event, S250818K, by Noah Franz just a few months ago. So this is just showing our web interface. It's based on a target and observation manager we've been using for many years now, but just showing a probable transient that initially we thought could be a kilonova associated with this event. And we can sort of break down the score into different components, saying this is actually how we calculated it, just trying to be as transparent as possible with people potentially using our tool. And so we used this and calculated scores for all of the transients that we were following up. You can sort of infer that the scores are going to change over time as new photometry or information comes in. And so this is what we thought was a high probability kilonova candidate. But even at the very earliest time, there were other sources in the localization region of this S25 event that were more probable to be kilonovae that just didn't receive any follow-up. So we're hoping that this TROVE tool will be able to help other optical astronomers optimize their follow-up, sort of aggregate information, and better coordinate what we think are the next kilonova candidates. So we actually have a website with our beautiful AI-generated logo. It's on datatrove.as.arizona.edu. You can actually go to this website right now. There's not much going on, but we're hoping to deploy the sort of beta version of our tool, and we're looking for beta testers probably this summer or early this fall when LIGO turns back online. So with that, I'd just like to summarize. In 2017, we isolated for the first time a source of the R process, but many open questions remained as to how much ejecta it produced, how common these types of events are, what the underlying physics were that actually produced this event. And more recent GW observations have shown us that the neutron star merger rate might not be as high as we actually thought back in 2017. So we're actively searching for other sources of the R process, either from very exotic transients, magnetars, normal supernovae, something where we can pinpoint some other source of this heavy element production. And then finally, I'm actively working on a number of tools, including with Manisha, just to better optimize the follow-up of these gravitational wave sources and find the next source of the R process in kilonova emission. So thank you, and I'll take any questions. Yeah.
Thank you very much. It was a very beautiful overview. I think it was really exciting to follow the story. So, my question is about the fate of material that's ejected as our process elements, and as in, so I imagine, so the first neutron star merger candidate was quite far away from the disk of the galaxy, exploded quite far away, and not only that, the mergers eject speed at material at the speed of like I don't know 0.1 speed of light, meters per second or so. So
Yeah.
It's well above the galactic escape speed, especially if you play something far away. So I mean, I could imagine that the double star merger happening close to Milky Way would probably eject much of its mass into the intergalactic space, and likewise, if some mergers from near other galaxies would be also doing that. So I mean, probably some would extra come from outside, but also some would be lost to outside. So what do you think is that? So will we get more than it should have, or less?
Yeah, it actually might even be worse than you imagine because, even though it looked kind of like that event was far outside the core of its galaxy, it was very close by compared to a lot of other, for example, short gamma ray bursts, where we observe up to tens of kiloparsecs away, we think, from their host galaxies. And in that galaxy, it was in a very low density environment, so you don't have a huge amount of matter where it can sort of plow into like sort of a normal supernova entering the set of Taylor expansion and decelerating. The one thing that sort of helps the material stay in the galaxy is there's not very much mass, and so the total kinetic energy in that event, even though it's traveling at near relativistic or even relativistic velocities up to about 30% the speed of light, it's less energy than a normal supernova explosion. So I think most of it probably does end up mixing into the galactic environment. It's very stochastic, of course, because these events are really rare. But over time, over billions of years, it's either going to get decelerated and just mix into the interstellar medium, or as you said, sort of rain back down onto the galactic environment. But that's actually something that a graduate student at Arizona, Anya Nugent, has been pursuing with different galactic environments of gamma ray bursts and with 0817. But it's still kind of an open question exactly, at what rate does the R process mix back into the host galaxies?
I follow up just like what do you think about galaxies exchanging our process elements with other galaxies? Would the more massive ones like Milky Way benefit from this process, or would they kind of be a disadvantage?
I mean, most neutron star mergers are going to occur in sort of the densest stellar environments. So that, I mean, that was what NGC 4993 proved. So I would expect it's actually kind of difficult for me to imagine in environments like Reticulum 2 how they get such a high abundance of our process material unless one of these mechanisms, like you're describing, obtains and it sort of mixes into the intergalactic medium and then rains down on low mass dwarf galaxies. But I think that's sort of an open question about how exactly that mechanism works. Yeah.
I want to drill down on this idea of our process crisis.
Hmm.
The binary neutron star merger rate point estimate has gone down since 1717, but the error bars were very large.
Hmm.
And my understanding is that the error regions today and then nominally overlap two signals like this.
Yeah. That's right.
So if we accept that premise, and given that there are other uncertainties going from the gravitational wave rate to the merger rate out there, like we don't know the mass distribution of binary neutron stars, we don't know how they evolve, the merger rate revolves with redshift.
Hmm.
How confident are you that there's actually a crisis in that the idea that binary neutron stars aren't playing a major role in our process? I'm quite open to the possibility that they're not, but are you really?
So I guess the calculation that we performed in 2017 was sort of the most basic thing that we could do, taking the median rate of neutron star mergers. And so back then it was about 1500 per gigaparsec cube per year. And the most recent sort of median rate that I've seen estimated from LIGO people is about 30. So that's a factor of 50 different. So I'm very, I guess in that sense, just sort of zeroth order estimate. I think there potentially is an issue, but I think part of the solution actually is that neutron star mergers are the most efficient place to produce the very heavy elements. The really I didn't mention this, but there's three peaks of the R process, first, second, and third, with the third being the heaviest elements of the lanthanides and actinides. I think neutron star mergers probably dominate the production of that material. And we were actually most sensitive to that material because those are the ones that have the open F shells and are very difficult to produce unless you have a very low electron fraction in the ejecta. But the elements that I mentioned that we're looking for in Cas A, those come from sort of the first peak of the R process and are potentially easier to produce in sort of a instability on the surface of a neutron star or these exotic supernovae like Manisha is studying. So I think there's potentially a crisis in the light R process, but I would say probably not with the heaviest elements.
Thank you.
Yeah, Alex.
Maybe normal supernovae make some of this R process. With my recollection of history, that before this binary merger was discovered, this was actually a standard picture, the standard paradigm where the R process comes from in the first place. So it's basically just going back to square one again after.
Yeah, I think you're exactly right. And actually, Stan and Woosley has worked a lot on this. The magnetorotational instability in core collapse supernovae, or yeah. Well, and I think we both know a lot of people who would say jets are responsible for all supernovae. I don't believe that, but I think it's possible to produce a jet or an instability that disrupts some of the central compact object in potentially most core collapse supernovae. And so it's sort of a question of how much material gets ejected, how much of it actually mixes into the iron and excites the R process, and how can you keep the electron fraction low enough in that innermost material, where you have a huge neutrino flux, you have heating from radioactive elements going on in order to cause the R process to be very efficient. I think that's still very uncertain, and I know like Dan Siegel is still working on that, but maybe these JWST observations will demonstrate that we should have been listening to Stan and other people talking about the MRI the whole time. Yeah.
Optical element, really the assumption that it's somewhat universal star within the galaxy.
Yeah.
Is there a difference between LMC stars versus Neutron, or?
It actually tracks very closely to the solar R process abundance. So there's some variation, and it's actually a little bit difficult because these observations are mostly pinned to europium, which I'm pretty sure is a second peak R process element. But that's really like the main measurement that we have to say there's some R process in these stars, and that gets mixed in very early in the universe. And while there's a little bit of variation in these dwarf galaxies or, like in the LMC, like you mentioned, it's close to the solar abundance profile or what we see, for example, on Earth. Oh, yeah.
You kind of slipped this in your slide in the type 1 section, but
Mhm.
you asked something very briefly about AGNs as a host of binary black holes.
Yeah.
It's a very contentious.
It is very controversial.
You get these electromagnetic counterparts from binary black holes. But as an electromagnetic observer, I'd love to hear your thoughts. If you spend some resources even thinking about them, you
Yeah.
think a little bit seriously. So what do you make of this idea, both from a theory perspective of producing these electromagnetic transients with no neutron star, and also observationally, what do you think about that?
Yeah, so I'm sure you're aware there was this S190521G event that the Caltech group led by Matthew Graham. They found potentially an AGN flare that occurred after a binary black hole merger. And what was interesting about the merger was that it was very high mass. So it was exactly the kind of event where if it did merge in the disk of an AGN, you would expect one of these short period flares in an AGN disk. So that was really what motivated us to follow more binary black hole mergers. That and the fact that my colleagues at CBPF in Brazil, they do cosmology. So if we have more well-localized events, we can do dark siren cosmology, or sorry, bright siren cosmology rather. So I think initially when we were first doing this science, it was sort of favorable because I'm not sure how much you know about AGN disk models, but it used to be that people thought the disk in the center of AGN were very dense in material in these thick disk models. And that, in fact, so dense that the star formation rate must be very, very high, that they're essentially using up all of the gas in these AGN and producing loads and loads of binary black holes. More recently, Phil Hopkins, also at Caltech, has been revising some of those models, saying that the magnetic pressure in AGN disks actually causes them to be a lot puffier. And so the star formation rate probably isn't all that high in AGN disks. But those two facts motivated us to think that, one, this is a likely scenario. Two, it's going to occur a lot after binary black hole mergers. Three, we can do cosmology this way. I think it was very hard to do with our small telescopes, but if it is happening, we'll sort of get these observations for free with LIGO plus LSST. And that's probably a better way to do it anyways.